that we utilize when implementing the embedded systems. So today I would want us to look deeply and see what are the physical components of these embedded equipments. Actually, they are the two main chips that we will be able to use to implement a workable embedded system. So we want to look at the embedded system components. One will be the Raspberry Pi, and the other one will be Arduino system. But all in all, both components are implemented using the same architecture, even though the architecture might vary in terms of additional component in each and every board. So for that reason, we would want to look at the general components of devices that are being used to implement the embedded system. So I'll pick up from where we left yesterday, and I would want us to look at the microprocessors and the microcontrollers. So to initiate, basically we need to know what are some of the components that are there on the embedded system board, which basically are used to implement various IoT of things and actually the embedded system controllers. So we are going to look at the microcontroller as being one of the components that we need in this particular environment. And we need to understand what is a microcontroller when it comes to embedded system. And you'll realize that a microcontroller is a unit by itself, and it is a computer on a single metal oxide semiconductor integrated circuit chip. So basically what you need to know is that a microcontroller is just a chip, and this chip is made up of a few more components for it to work as a unit. So you can say basically a microcontroller is just like a computer that has components that make it function at the end of the day. Microcontrollers contain one or more CPUs. So you would have a scenario whereby you've looked at your computer system and you notice that most of the computer systems, more so high-end computing system, they will be able to have like two processors and have several banks of RAM. That's the primary memory. So in this scenario, you'd also need to understand that a microcontroller, since they are sharing the same architecture or the same system architecture with the normal computer system, you should also know that they can have more than one CPU, or what we call the processor. So a microcontroller contains more than, it can have one, it can have two, it can have three, it can have several. So it has them along with the memory and programmable input and output peripherals. So memory here is what we call both the RAM and the ROM. So we are going to see where these two components come in embedded system. So we also have what we call programmable.
Excuse me.
Yes.
Excuse me on this.
Yes.
Are you presenting because we can't see anything?
Okay. Oh, you can't see my screen. Sorry.
Yeah, on my part, I can't. I'm not sure about the rest.
Let me just have a look at this. Because we pull directly from the classroom. Okay, let me just do this. Let me just do this. Okay. Can you now see my screen?
Yes, can.
Okay,
Yes.
sorry. Okay, sorry for that. So, as I was saying, that the microcontrollers is basically, it contains more than one CPU. So you can have more than one CPU sitting on the integrated circuit. So that integrated circuit can be able to have the processor, it can be able to have the memory, and at the same time, it can be able to have the programmable input-output peripherals. So why do we refer to them programmable input-output peripherals? We call them programmable input-output peripherals because we are the one to control what goes in and what is to be displayed. And that is where the programming language come in. I would want to say that I want my pin 1 to produce this kind of a pulse. I want my pin 2 to produce this kind of an output. I would want my pin 3 to do this. So that is the reason why we call them programmable input-output peripherals. So you need to understand, why do I call them programmable input-output peripherals? So so if you can look at that that chip, that integrated circuit chip, that is an example of an Arduino board or an Arduino integrated circuit. This one here, and then the other one on my left, on my right actually, is what we call the Raspberry Pi board. So if you look at these two boards, they have several chips on them, and we are going to see each and every chip, what is the function of each and every chip. And again, on the end, you'll see some pins on the Arduino board, both left and right. And also on Raspberry Pi, you would see there are some pins, both left and right. So these are the programmable inputs and output pins that we are going to see. How do we program these pins, and how do we use them on a normal programming or a normal embedded system development. So microprocessor. So you know what a microprocessor is from your knowledge of computer systems. This was sometimes in the second year. And one of the things that you know is that it is an integrated circuit, meaning that it is a board, an IC circuit that contains all the functions of a central processing unit of a computer. Or it is a computer processor where the data processing logic and controls is included on a single integrated circuit. So that means that there's data processing on that circuit, and there is also what we call the control. The control is the flow, the operas, the expressions, the ands, the ors, the nands, and so on. Those are the things that you are doing in digital electronics. So you'll see the logics come in and also the controls come in. So if you understood your embedded, your digital circuit class well, you'll realize that there is what we call controls. And how does controls work? There are those things we call logics, and how does logic works? So all this is implemented on the microprocessor. The microprocessor contains arithmetic, logic, and control circuitry required to perform the functions of a computer central processing unit. So I would want you also try to look at this particular microprocessor as you are looking at the ANDs, the OR, the NOR gates that you are doing in digital electronics. Try to put them together, look at how it works, and then you can now come back to the processor and actually actualize that thought. So basically, from the image you are seeing, this is how the microprocessor looks like. And I believe that most of you have seen how a microprocessor looks like. In this class, do we have students who have never been in contact with a microprocessor of any type, be it a reduced technology microprocessor and a very large interface system like the CPUs and the servers? So do we have students in this particular class who have not been in contact with the microprocessors? Is there any? Yes? Derek Kipron, do you know what a microprocessor looks like?
Yes.
Have you interacted with one?
Yes.
Terry, do you know how a microprocessor looks like?
Yes.
Have you been in a position to interact with one? And which one?
It was in an Arduino board.
So apart from the one that sits on the Arduino boards, have you interacted with any in terms of the PCs and the server processors?
Not yet.
Yeah, so I believe we'll need to maybe have a session whereby I will be able to show you how these microprocessors looks like. And I would also want you to be in a situation whereby um, uh, you interact with them and you see how the pin systems are made up and how the pin systems actually functions. So that, to me, I think it's core, or it's very important in terms of learning and understanding the embedded systems well. This particular class, we've always generate a few exercises to be looked at. And these exercises, I would always ask students to take them seriously. If we're done with the class, you need to go back and look at these exercises and see, to help you understand fully what we have been learning in class. So I would want you to take your time and discuss the notion of embedded system. What is embedded system? Basically, you can read more and actually understand it deeply, and have a clear concept of what embedded system is. I would also want you to discuss the notion of mobile application development. What is this thing called mobile application development? What does it entail? What is the workflow? How does it move from the initial point to the execution and actually to the end? So you'd also need to discuss the notion of cross-platform mobile application development, whereby we did say yesterday that you can have one application that cut across all the mobile application devices. It can run in Mac, it can run on Windows, it can work on Arduino, it can work on the HTMLs, environments, and so on. So I would always want you to look at these exercises, take your time, do them, read more about them to help you understand clearly what embedded system is and what mobile programming is all about. So is there any question up to there? Anybody with a question? Okay. So what are some of the areas in which you can be employed, or what are some of the jobs that run around the embedded systems? So the firmware engineers, so what does a firmware engineer do from your understanding? Anybody who understand what a firmware engineer does? Yes? Edith Nike, what does a firmware engineer, what's the function of a firmware engineer?
Firmware engineer creates, I'm not sure, but I believe it creates the devices or the program that are embedded into them, the
Okay.
low level software programs.
Okay. Hashim, how do you understand the word firmware engineer? Rama? Dak, who is a firmware engineer?
From my understanding,
Yes.
like for example, like laptops usually get firmware updates, which basically, like I think just like tell the computer, oh, in this update, we can do this differently, and maybe we change this on how the computer should work. And I think a firmware engineer writes all that code.
Okay, so that basically makes a lot of sense. So a firmware engineer would be somebody whose basically his main job is to ensure that every update that comes into application which is already developed is upgraded. You can use firmware to be able to fix bugs. You can be able to use firmware to do an upgrade. You can be able to use a firmware to enhance on how that particular application works, or a particular components operate. So firmwares, people we call the system engineers. So system engineers are guys who basically do the normal overall system development, not really development, but system maintenance and system upgrade and system deployment. So if I would want to build up what you call maybe a base station, then one of the people that I need is a system engineer, because you'll be able to know which components go in where and which components interact with which components. So there are freelance jobs. The embedded engineers is a highly demand job. The rise of products like refrigerators, smart home systems, connected devices with using more software. So if you want to have your refrigeration will behave in a different way, you want it to cool to a given temperature and does not surpass a specific temperatures, then you'll be able to initiate the embedded system on the thermostats. So when the thermostat knows when should it go up, and the thermostat will know when it should go down. So it is very important that you know exactly where do you introduce the embedded systems in your refrigerations, and where do you introduce the embedded system on your smart home system. And when we talk about the smart home system, we're talking about you'll have the cameras that are around your house that monitors the movement. Which kind of movement? If a cat jump from one home or from one fence to another, should your system pick, or should you teach your system that that is just a normal cat that lives with us? Ignore. You don't raise an alarm. If somebody is trying to break the gate, to knock the gate or push the gate in a way, so you'd also be able to impact how much force or how much knock is allowed. So all that areas you can be able to implement within your home setup. Technopreneurship. Your embedded system knowledge can make you convert hardware projects into a product that you can manufacture in large quantity to sell out to the market. So you can be able to work on embedded systems on your existing product, and from there you can be able to market it up, and it can solve a day-to-day problem. So you should always be very keen. What am I working on? And if I'm working on this thing, what is the day-to-day solution that I can be able to get, that I can be able to sell to the public or to other people to also to consume. So some of the real life application areas for embedded systems, as we had seen this also in our previous class. So there are home appliances, the audio play, the integrated system in aircraft and missiles, the cellular telephony, and the cellular telephony is an area where embedded system, AI and machine learning is actually being used. The IoT of things is seriously being used in the cellular telephony today. Electric and electronic motor controls, so the engine controllers in automobiles. There's calculators that you use to do arithmetics. The medical equipments, uh, the video games, the digital music instruments, and so on. So all these actually have the embedded system component within them. So some of the real life application areas of embedded systems, as we have seen all those areas, so we have quite a number of parameters that one will be able to use embedded systems in. So all these areas, there are so many. So you'll have a look at all those parameters that utilize the embedded system. So we'd also want to look further now, because we had said that the processors or the chips that are being used on our microcontrollers are from what we call the ARM ARM 0705. So M version. So the M versions come with the M0, M3, M7, M5, and so on. So what are these? We need to understand what are these ARM microprocessors or ARM controllers that are used on our Arduino, on our embedded system. So ARM basically is advanced RISC machines based processors.
We can't hear you on DT.
the
So
VLSI technology.
usiku umeanza kujiongelesha tena. We can't hear you. On my part, I can't. Oh, umeenda.
His internet is acting up.
Yeah. If you are speaking on DT on my end, I can't hear you.
Oh, can you hear me now?
Yes, I can.
Okay. So as I was saying that the advanced risk machines were first, they came in the late 80s, and this development came from Apple computers, and they're using what we call the VLSI, what we call very large scale integration technology, that actually started their work in the Acon. So Acon is a big company that's developed chipsets in the United States, and they major mainly in creation of very high speed chipsets. And they're the ones who came up with a new version of the ARM course. So in the 90s, the Acon spun off the design team into a new company name. And this is whereby the name ARM came up, and it was called the ARM Limited. So the new Apple ARM work would eventually evolve into what we call the ARM6, which was first released in 1992. So this basically was the very major processor that was put in on the first Apple machines that were introduced then. So the Apple machines used what we call the ARM6, and it was based on ARM 610 as the basis for the Apple new PDA. So this terms that basically were used to define several microcontroller which was put within a circuit to implement the core, which is actually the processor for the embedded system. So the ARM, which was advanced risk machine, is a reduced instruction set computer system that typically have attributes like large array of uniform registers, have what we call a load and store model of data processing, where an operation can only operate on a register and not directly on the memory. So when you are learning computer architecture, I believe you looked at what we call the risks, which is reduced instruction set computers, and the CISC. Yes, so those were the two major ones. So the RISC and the CISC, these are the things that you looked at when you're doing your computer architecture, and these two parameters would be able to have what we call uniform registers, and you know the function of the registers, have what we call the load and the store model of data processing. These are key in terms of developing a register that is being utilized by a system. So in most cases, you need to understand what is a risk system and what are the components of a risk system. So this requires that all data be loaded into a register before an operation can be performed. So basically, there's what we call the input-output registers and what we call a buffer. registers. So the function of the buffer registers, the function of input-output registers is basically to hold the instructions that are supposed to be executed by the microprocessor. So a small number of addresses modes with all loads and store addresses begin to determine from the register and instruction feed. So remember, within the microprocessor, we have several buses. We have what we call the control bus, we have what we call the address bus, we have what we call the data bus, and those three works hand in hand. So one, the control bus, what's the function of a control bus? What is the function of a data bus? And what is the function of we have data bus, we have address bus, and basically those two and are the major components that we actually require within a register. So these buses sits within a register and they'll be able to carry instructions from one place to another, and they have a length. So what we call the uniform fixed length of instruction. So when we talk about the uniform fixed length of instruction, that we are talking about how much instruction can be able to send within a bus. So this bus can only carry this much. So after that much, then the others are pushed to the buffer and then waiting to be resent to the register for the purpose of for the purpose of execution. So you also need to understand how much data can a bus carry. So a bus that can carry more instructions is much faster than a bus that can carry less instructions. And when it comes to the what we call the uniform fixed length instructions, this is whereby you were able to discuss the issue of a 32-bit or a 64-bit system. So there's a microprocessors which are 32-bit and there are microprocessors which are basically at 64-bit. But what determines that is the length of the bus. So if the bus can be able to carry 32 instructions and buffer the same number of instructions, then we refer to it as a 32-bit instructions bus. If it can be able to carry a 64-bit and buffer the remaining 64-bit, so once these ones are executed, then the other ones are sit in the register and also being pushed for execution. So those two parameters would always define the speed of a microprocessor, and that sits on what we call ARP, what we call advanced RISC machine. And when we talk about RISC, we are talking about reduced instruction set computer. The instructions, how are instructions handled within the microprocessor between several components or logical components of the microprocessor. I would want to pause there so to be able to pick a few questions from you guys. So if somebody has a question, now this is the right time that I would be able to answer it. Any question? Yes, so it seems everything is okay. So we need to continue. So ARM are attributed typically to that type of a system. And in addition to this, a traditional features of a risk system, the ARM provide a number of additional features. So one of the features that ARM brings in is that it has come up with a separate arithmetic logic unit. And I believe you know the various components of arithmetic logic units. Um, and it has the additional control over data processing to maximize the execution speed. It also have what you call the auto increment and auto decrement addressing mode to improve the operation of the program loops. So what this means is that within the address bus, if I am having an address bus which is a 32-bit, so it is able to have data sync in such a way that if additional instructions are sent within a loop, then within the registry buffer, it can be able to sync them in such a way that it expands the cache within the logic unit to allow more instruction to be sent. If the less instruction are being sent, then it reduces the workability or the impact of this particular device. So that basically reduced by default. So there's what we call conditional execution of instruction. So basically to reduce pipeline flashing and thus increase execution. So the other thing that you need to understand, what do you understand by pipeline flashing? So pipeline flashing is a scenario whereby there are instructions. So assume you have an instructions which is, for example, it is 12-bit. So this instruction is less than what needs to go in. So what happens, it is pushed back on the buffer and then awaiting, creating space within the execution zone, then creating more space so that once it gets into the execution areas, then you have a whole mode of program to execute. So this is a scenario whereby you do not have less instruction being sent to be executed, yet it can be able to carry more. So it has a scenario whereby if there are very little to be executed, then it is kept within the buffer. And then once all the instructions reach the maximum, which is 32-bit, for example, if this is a RISC, which is a 32-bit, then it's when it moves to the other end. Then it removes everything within the pipeline. So there's no instruction that is left within the execution zone. So once that is done, then another pack is brought in. So if it is a 32-bit register, it can only ensure that it executes 32-bit at a go. If the instruction given to the microprocessor is less than that, and there is no more sitting behind, then that is the only time you realize that this particular type of a microprocessor will just execute and clear everything within the pipeline. So the other thing that you need to understand also that I need you to take time and read is you need to read more about the arithmetic logic unit within the risks component and see how do you introduce what you call flashing and increase the speed of that type of a microprocessor. So the ARMs have contributed to the present day smartphone solution or revolution, and ARMs, its partners have enabled more integration and low power, giving rise to what we call the ARM11 and the Cortex A series CPU core. So these are very small microprocessors, microcontrollers, which are actually implemented using what we call the ARM technology. This core have revolutionized and continue to power many smartphones. So when you look at your smartphone, more so the Apple smartphones, they have been developed in such a way that
Hello.
yes.
And there's a lot of background noise, which is a bit distracting from my end.
I'm having background noise.
Yeah, a lot of like there's a child crying and such.
Yeah, I'm where I'm working. There's an hospital next, so I think that is it. So let me just see how I'll sort out that. I'm actually sitting somewhere within the hospital as I'm doing this, so um, I hope it will just moderate as time go by.
Okay.
Yeah. Okay, so we can continue. So as I was saying, that you should understand that the ARMs processors are basically used to implement the core, the microcontrollers that we use on your mobile phones today. So the ARMs just focus on building ever smaller. The ARMs, they keep on reducing because, as we say, it is a reduced instruction set. So they keep on ensuring that they have lesser and lesser or smaller and smaller chipsets that can actually be used to be implemented on different types of portable equipment. And that's why you see it is suitable for embedded systems, because embedded systems need to be small chips that can easily be programmed and at the same time do a huge amount of instruction setup and controls. So the more the reduced instructions on a microprocessor, the more powerful it becomes. So, and as I've said that, what happens is that they try to work with what we call the registers, they try to work with what we call the arithmetic logic unit, and they're trying to work with what we call pipelines. So if they want to reduce the amount of content that remain in the pipeline, and anything that remains in the pipeline should be removed within the shortest time possible, so that more instruction can be able to send. So as that grows, so the RMM, they are just focusing on building ever smaller and even lower powered microprocessors under what we call the Cortex-M brand. And you saw when we were introducing, we say that the Cortex-M brand are ARM Cortex-M brand. So basically, it is one family that manufacture this type of processor. So the major families of the CPU core before Cortex-A applications. So there were Cortex-R, which is real-time processors, and Cortex-M, which is embedded and microcontroller chipset. So the ARM, you should be able to see, there are actually three. There's what we call the application, the real-time, and what we call the embedded system. So you need to understand those three parameters. So any question up to there? So is there any question from your end? Anybody who has an area that is not getting right? So in a nutshell, one needs to understand how the processor or how the microcontroller that is being used to control the Arduino boards, the Raspberry boards are implemented. One, you should be able to know that that particular microprocessor is implemented using what we call the ARMs. And two, the ARMs come in several versions. So we have what we call the application processors, we have what we call the real-time processors, and we have now what we call the embedded system processors. So the M is becoming increasingly important as compute is added to more types of devices. So you'll realize that more computes, more controls are added in several devices, and the M component is what is becoming key in some of these new technologies that are coming up today. So all these three families can be within one chipset, and implemented using one processor, but the M component is being added in almost every device that need to have the embedded system within it. So you need to understand well how does microcontrollers build to be able to be controlled or to be able to be programmed to do several work in terms of embedded system. So we have that. So the ARM Cortex processor across embedded market. So we have the M processor, we have the R processor, and we have the A processors. So these are three different families of processors. So they are low power, and actually most of them consume between 0.5 volt to 20 volts. So as time go by, we are going to see what is what. So when you're buying these microcontrollers, you should be able to know which microcontroller am I buying. Am I buying the one that would be able to have what you call the M processor? This basically doing the M work. This is the embedded and embedded computing. Am I going to get one which is R? R is the one that does what you call the real-time operations. And then we have the A, the applications, the application processor that basically do it's for high performance. So you really need to know when you're going to the market to buy a microcontroller, you need to be very sure. I want a microcontroller that will be able to achieve, you'll be able to use it to achieve your objective. You can go to the market and buy a microcontroller, and then you go to the one which is called an A processor. But this is just for application processing. But if you want to do the embedded system, then it must have the within it. So you must be very careful. What are you buying, and is it applicable to what you're going to do? And if you realize that even Arduinos, when you go to the market, there are different types of Arduino boards. So you must be sure, am I buying the M ones? Am I buying the R ones? Or basically the application version of the board to implement what you want to do with your project. So I have an architecture here of ARM-based processor. And from this, you can be able to see the arithmetic logic unit down there, and it's given 32-bit arithmetic logic unit, meaning that it can only execute 32 bits of instruction per given time. So we have the control unit, we have the MBR memory buffer zone up there, we have the memory address register up there, and then we also have the address incrementer somewhere at the middle. So when you look at, basically you look at the arithmetic logic unit, you'd be able to see you have registers, you have controllers, you have addresses, and you have the memory. And from there, then this basically is the microcontroller, the black dark lines. This is the microcontrollers. And then from there, it has attachment to the external memory. So the external memory here is where we have the RAM, we have the ROM, and so on. So once this instruction has been executed, then it needs to be pushed to the external memory, awaiting to be output. So when you do an input-output, the first thing that gets contact with you is the external memory. It gets the instruction, then push it to the microprocessor. When the microprocessor has executed it, then it takes it back to the external memory, then the external memory would be able to display it out there. So that's why I was saying you basically need to understand how does your pins work, because we are going to program these pins and you'll be able to tell where do I put which instruction and for what purpose do I want to achieve with it. So the Cortex M7 targets applications. So an high-speed MCU, automotive, sensor hub, IoT of things, and industry. So these are some of the areas that highly target the ARM M version processor. So powerful processor for advanced audio, visual sensor, and hub processing. efficient local processor for IoT, and flexible and reliable processor for industrial and motor controls. So if you are looking at the microprocessor, you would also need to get this hierarchy right so that you get the right microcontroller to use to implement your embedded system. There's an overview of it down here. It's far much instructions on how this embedded system M processor is built. So I would want you to look at it more, read more about the Cortex M7, understand further about how its architecture is developed. So the ARM development workbench. So basically, this is when it comes to development of how the ARM functions. So there's the IDE tools, there's the build tools, and there's what we call the SPI debug. So this is basically the normal environment that you do within your programming or when you're developing an application using a given programming language. It goes the same way. So if you can look at the way your application run, you should also try to look at how the microprocessor execute instructions and then give us information at the end of the day. So there's a lot there that I tried to put in terms of what are the R's, what do they do, and so on. So once you get the slides, you'll be able to take your time and further look at this table and see whether it makes sense to embedded system implementation. Okay, so this is just what it means, what all those instructions labeled within your board means. So these are the algorithms that actually sample algorithms that are implemented within the microprocessor that I think we don't need to go deep into it. But what you really need to know is how does the loop work? What does sub GT or sub greater than means, sub less than means, and not equal to, and so on. So these are just a language coded in assembly language that the microprocessor implemented using ARM understand. So there are more of a block diagram of the ARM application attached here. So this is something, again, I don't need to go through it. It's just you to read it up and be able to understand basically how the microprocessor operates. So there's an exercise there that I would want you also to look at. I would want you to discuss and expand the variants of ARMs, the RISC acronyms, trace the history of ARM processors. I would also want you to try and describe where ARM processors are used, which we have actually seen in our discussion today. I would also state 5 instructions for the ARM processor. What are the major instruments for the ARM processors? You'd also want to discuss the ARM processor architecture. How does the architecture looks like? This is a fundamental area that I would want each one of you to look very carefully and be able to discuss and understand fully how that operates. So we have why are ARM processors relevant? So again, I would also want you to see what are the benefits of the ARM microprocessors when it comes to the Arduino implementation. So to me, I think that is key. So I would want you to look at them and be able to come up with something that is workable. So I would want to pause there and get questions from students. Anybody with a question? Anybody with a question? Amina Wanjiru.
I don't have any question.
Do you understand what ARMs are?
Yes.
Where to implement them?
Yes.
And the different types of boards that are implemented using ARMs?
Yes, I do.
Okay, that's good to do. Any other person? Let me go down here and see. Omai, Joseph,
Yes.
do you have anything to say?
No, the walkthrough has been comprehensive enough for me.
Okay, good. Tanya, can you say something? Tanya? No question. Joel?
I'm okay.
You're good. Alex Gay, do you have any question on embedded system microprocessor? Alex? Shadrach? Kiumba?
No, I'm okay.
Do you understand the different processors being used to implement the embedded application system?
Yes.
Roman Njuguna, are you present? Did you get the 3 different families of ARMs and areas where they can be applied? Good. Onyango Betley. Onyango Betley. Okay, so I think that's good enough. So I think we had a problem with our platform in terms of putting in this particular notes. So I don't know whether you are able now to see the folder from your classroom. Yes, the class rep. So I think we'll need to be in contact so that we ensure that this is sorted out before weekends, because by next week, I expect students to start working on their projects and groups. By the end of next week, I would want to see the form completely filled. We'll close it on Friday. So by Friday by Thursday, because Friday will not have a class, you ensure that your name is in the spreadsheet, and we'll pull down that spreadsheet and have a physical printed spreadsheet to be able to start monitoring and evaluating the progress of the project. Okay, so we stop in there unless somebody has a burning issue. Any question from the class? No question. So I can see we only have 49 students. I don't know where others are. Class rep, how many people are we supposed to